So in this problem, we're given a function and we're asked to find the local maximum in quadrant 1, which is closest to the origin. Seems to me the best way to go about this is to graph the function. In order to graph this function, you'll notice a couple of things. First of all, I have a negative sign function, so it's going to be an inverted sign. But more importantly, the argument has two transformations in it, in the sense that it has a subtraction and a multiplication. I've always found that the simplest way to deal with this double transformation in the argument is to factor out the lead coefficient of x. So in this case, I'm going to factor out a 3. Hit pause if you want to confirm this factorization. The point is, now that I have factored the lead coefficient out within the argument, it's now easier to discern that I have a horizontal compression by a factor of 3, followed by a rightward shift by 2 pi over 9. And of course, the reflection through the x-axis that comes from the negated sine function, as we mentioned earlier. So now let me take the sine function and perform all of these transformations. First of all, here's the inversion or the negation of the sine function. I've shown one period here from 0 to 2 pi. And next, let's deal with the horizontal compression by a factor of 3. This is physically what a horizontal compression by a factor of 3 looks like. Although, as I always say, I don't recommend physically compressing the function, when instead you could keep the same drawing, divide the pertinent points on the x-axis by 3, or the compression factor, thereby having the same effect as a compression by a simple rescaling of the x-axis and not having to physically draw something so compressed. Now let's deal with the rightward shift by 2 pi over 9. This function is going to shift rightward by that amount. This is one cycle of the new function. And since we're looking for the local maximum in quadrant 1, let's find out what this point is. Well, to find that point, it might be easier to put that graph aside and find this local maximum first. So let's focus our attention on that before we go back to the function we're actually interested in. First, I found that this local maximum occurs at pi over 2, which I found by averaging or taking the midpoint of pi over 3 and 2 pi over 3. The algebra is shown here, and you could work it out on scratch paper if you'd like, but that does in fact work out to pi over 2. And now that I know that that local maximum occurs at pi over 2, I can find the local maximum that I'm setting out to find here. You may see it as a green dot. It's the maximum on the far right. All I have to do is shift the function over by the 2 pi over 9 previously mentioned. I did that on scratch paper, and I got 13 pi over 18. Here's the calculation I did to get that, if you'd like to pause and do the math. Well, now I know that the function I'm interested in has a local maximum whose x-coordinate is 13 pi over 18. And thus, the coordinates of that local maximum are 13 pi over 18, comma 1, which comes from the fact that this sine function has an amplitude of 1. That's not surprising. However, while this point is a local maximum of the function that they gave me, it turns out not to be the one closest to the origin. And to get a better sense of this, let's extend this graph and the original graph before the shift further to the left. You see, something interesting has happened here. On the pre-shifting function on the left, you may see it in black, there was a local maximum. This local maximum we didn't talk about because it wasn't in quadrant 1. And the problem only asked about local maxima in quadrant 1. But funny thing, once that maximum shifted over by 2 pi over 9, that produced a local maximum on the new function, the one we're interested in, that is in quadrant 1. And so it turns out, while this point here is indeed a local maximum of the function of interest, it is not the answer to this question because it is not the closest to the origin. This newly found local maximum is the green dot that you see closest to the origin. So now I'd like to find out the coordinates of that point. That will be the answer to my question. Let me share my thoughts how I went about finding that point. It occurred to me that on the pre-shifted function, this is pi over 3. And so the mirror image x-intercept on the other side of the y-axis would be negative pi over 3. That puts the local maximum of the black function occurring at x equals half of that, or negative pi over 6. And I can take that local maximum, shift it to the right by 2 pi over 9, which I did on scratch paper, and found the x-coordinate of that local maximum. Here's the calculation I performed if you'd like to pause and think about that. And now I have found on the post-shift, or the function of consideration, I have found the local maximum closest to the origin occurs at pi over 18 and therefore has coordinates of pi over 18 comma 1. And that completes this very challenging problem.